Hi, welcome back to educator.com. Today we're going to be starting to talk about normal distributions. Now we're going to talk about normal distributions for the next couple of lessons, and it'll come up again and again in the future. So this is a pretty important one. All right, so first let's talk about what a normal distribution actually is. And we're going to distinguish it from what we've been talking about before when a distribution looks normally shaped. A normal distribution is an entirely different thing. We're also going to talk about how there are lots and lots of normal distributions, yet they all have the same shape, and what that really means. Then we're going to talk about some normal distribution problems, but only problems that use what's called the empirical rule. All right. So what is a normal distribution? Well, it's also called a normal curve, and a normal distribution really is a theoretical model. It's not based on data necessarily, it's a projection. So far, we've looked at frequency distributions, actual data points that have a normal shape. And by normal shape, what we really meant was symmetrical, unimodal, what else? Oh, that it had a point of inflection, right? Those kind of features. But they all just have a normal shape. They're not the normal distribution. The normal distribution, the actual model, is actually a probability density function. Now, when I draw a normal distribution, you might be like, well, that looks just like those normally distributed shapes that we looked at before. Well, the difference is that here, now this line, this curve, it's actually represented by a function that we're going to talk about in a later lesson. What's underneath the curve, the area underneath the curve, is the probability with which some value will occur. And so on the x-axis, we have some values. Presumably values of some variable. For instance, let's say height, right? So the values might be like 60 inches, 61 inches, right? And so here, what we see is the mean, the mode, and the median. But here in this area, that is the probability with which this value, let's see, the probability with which a value that's just plucked out of the world will fall in between x1 and x2. And so we're really interested in the relationship between the area and the values, right? And so that's what the normal distribution is really important, why it's really important, because there's this nice regular relationship between probabilities and values. All right, so let's talk about the range of probabilities that are possible underneath the normal distribution, or the normal curve. So the area underneath the curve represents probability. Now the entire area underneath the curve, if I colored everything in, that probability equals to 1, right? So all individual probabilities, this one, 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 all of these add up to, from negative infinity to infinity, right? Like all the way equals 1, right? Now, a probability of 0 means that that value never occurs. And by never, I mean like never, right? So what we're going to introduce is this new, well, sort of new notation. It might not be new to you if you've had probability before, but this just means that this is a probability function. Remember, we call it a probability density function. It's a probability function where given some value x, you get as the output the probability. So P of an exact score, a very particular score. So for instance, the probability of height being 60 on the dot is actually 0 in a normal distribution because it's a density distribution. It's not about frequencies, it's about probability density. And so what we're really interested in is the probability of score falling within a certain range. And that probability is not 0. And it actually doesn't matter how far out here you get, that probability is not actually 0. It might be like 0.00000000001, but it's not 0. All right, so the normal distribution, we could summarize it in a couple of ways. We could summarize it using the mean and the standard deviation. Here we see that the mean is represented by the mu sign and the standard deviation is represented by the sigma. Now if you recall back to populations versus samples, this is much more like a population than it is a sample. And that's because the normal distribution is a theoretical model. It's not actual data. It's a theoretical model, a projection. It's very similar to a population. It's where we think the samples all come from. And so some properties are just like the normally distributed shape that we've looked at before. Symmetrical, unimodal. Another word here is asymptotic. This is just talking about this fact that it actually approaches but never quite reaches 0 probability. So it asymptotes with the x-axis. So it comes real close, but doesn't actually touch it. And the final thing is that it's continuous. The normal distribution actually goes from negative infinity to infinity. Now, most values and most measurable things in the world don't actually have values from negative infinity to infinity. For instance, height. We don't really have anybody who's infinite height, right? Or negative height, for that matter. But the normal distribution stretches on forever and ever. Now, there are going to be what seems like a lot of different normal distributions. For instance, you might see normal distributions that look like this. You might see normal distributions that look like that. You might see normal distributions that look like that. And you might see them as having slightly different shapes, right? Like this one is sort of fat, this one's sort of skinny, this one's even skinnier. But you do see that each of them are symmetrical, unimodal, asymptotic, and continuous. But actually, there's more to the normal distribution than that. It's not just those 4 features. There's another property that it has, and that's going to be called the empirical rule. All right, so we talked about how they could be fat or skinny, but not all shapes that look like this is a normal distribution. Let me show you why. In a normal distribution, it follows some strict set of relationships between the probabilities and the values down here. And that's going to be important. Here's what I mean. When you go 1 standard deviation out from the mean, or the line of symmetry, when you go 1 standard deviation out, that area right here, let me color it in red to fit with what I have down here. This area should be about 34% of the curve, right? And that's always the case in a normal distribution. So let's say we have this shape, and it looks like a normal distribution, right? But we go 1 standard deviation out. Now let me draw it so that it's more exaggerated. Let's say we go 1 standard deviation out. Oops, it's very not symmetric. All right, so let's say we go 1 standard deviation out from the normal distribution. All right? Does this look like just 34%? Doesn't it look like more than 34%? That means this is not a normal distribution, even though it sort of looks like one superficially. On the other hand, let's say we have something that sort of looks too skinny to be a normal distribution. But if, in this case, going 1 standard deviation out looks like that, that is sort of 34%-ish of the total curve, right? And because of that, even though it looks sort of too skinny, it actually is a normal distribution. Whereas this one, it looks like a perfect, very typical normal distribution, but it's not because the area doesn't fit. So that's one thing you need to know, that 34%. Now, if you flip around that side, because it's a symmetrical distribution, if you flip it around, from the area between 0 and a standard deviation of 1, positive 1, this is also 34%. So when you add those together, it's about 68%, right? So just by going about 1 standard deviation out on each side from the line of symmetry, you should get about 68% of the area covered, more than half, right? Now, if you go out another standard deviation, right, and you look at the area between 2 standard deviation out and 1 standard deviation out, that area equals to about 14%, 13.5, right? And so let's write this in our new notation where we use P something something, right? So here we would say P, and I'll just use these as my values for now. I'll say P of where x is in between 0 and 1 equals to about 0.3413, right? And the area in between 1 and 2 equals 0.1359, right? And so this is how we would write this in algebraic notation. Finally, let's cover this small area right here, where now we're going 3 standard deviations out. And I'm just going to write my notation down here. Here I'm going to write P, where in between 2 and 3. And that area is about 2%. Right? And so here, this is what's called the empirical rule. I advise you actually just to memorize these 3 numbers, 34, 14, 2, right? Note that by knowing this, you could know at least approximately how much of the area is covered by going 1 standard deviation out, 2 standard deviation out, and 3 standard deviations out. Now, because we're rounding, if you add all these numbers up, 34, 34, 14, 14, and 2 and 2, you actually get 100%. But remember, the normal distribution is asymptotic. It's continuous, right? So it's actually a little bit less than 100%. So it's 99 point something percent, right? And there's a tiny, tiny, tiny little bit of area that goes out and out and out forever. All right, but it is sort of handy to know that around, if you go around 1 standard deviation out, then you'll cover 68% of that total area. If you go 2 standard deviations out, that's about 95%, little like 95.5%. And when you go out all the way to 3 standard deviations out, you get 0.9974%. So really close to 100%, but not 100%. And that's really important for the normal distribution. All right, so now let's talk about the different types of problems that you might be able to solve just by knowing the empirical rule. Usually in a normal distribution problem, you have to first look for whether the distribution that they give you is actually normally distributed. If they don't say it's normal, then you can't use the empirical rule. So let's read a prompt and let's look at what the different kinds of problems might be. So the distribution of SAT scores for math for incoming student to a university was approximately normal with a mean of 550 and a standard deviation of 100. Bingo! So they told us it was approximately normal. Yay! So we could use our empirical rule. And usually in normal distribution problems where you need to use the empirical rule, they'll probably give you the mean and standard deviation. In other problems with the normal distribution that we'll look at later, they won't give you the mean, and you might be able to figure it out. Okay. Then they might ask you, what percentage of scores were 450 or below? Here they give you the score. And you're supposed to find the probability of getting that score or below. So P, where X is less than 450. So note here what's missing is probability. Another question they could ask you is with the same prompt above, but they could ask you, what math score separates the lowest 2% from the rest? Here, they give you the probability, right? And what they actually want you to find out is what is the score. So what is this blank right there, right? So here, we're missing the score. So here I'll write missing probability, right? And here, we're missing score or value. All right, so now let's try to solve these two problems just by using the empirical rule. So what percentage of scores were 450 or below? Well, it helps to sketch out a normal distribution first. Here's 550, that's the mean, the point of symmetry. And 450 really is just one standard deviation away, which is 100, right? So the distance is 100. So you could think of standard deviations as sort of new units of measurement, right? So before we knew about inches and centimeters, now we're interested in how far away things are in terms of standard deviations rather than inches or feet. So here, the standard deviation is 100. And we know that even though these are the scores, or what we call raw scores, we know that these, in terms of standard deviations, this means that it's one standard deviation away on the negative side. And so we could just draw a little border here and sketch the part that we need to find, right? And that's the area we need to find. And we know that this part from here to here is 34%. We know that this part is about 14%. And we know that this part is about 2%, right? So we could just add 14 and 2 and get that the probability where X is less than 450 equals about 16%, right? So that's the percentage of scores. Now what about when we're missing a score but we have the probability? Well, let's sketch this one out as well. So here we have this 2%, right? And we want to know what is this value right here, right? Now we know that although we don't know the raw score right now, we do know in terms of standard deviation that at about in between 2 and 3 standard deviations away, that's about the 2% mark. And just to show you, I'll draw out the other ones. So in terms of standard deviation, here's 0, here's -1, -2, and around here is -3, right? And so this seems to correspond with about being 2 standard deviations away on this side. Now we know that this middle is 550. If we take a standard deviation, a 100 jump, that this would be 450. And so this value would be 350. So that's a little small, but I'll write it up here. So we know that what we're really looking for is 2%. That equals the probability. No, I should probably write this closer. So this 2% equals the probability where X is less than 350, right? And so, so far it's been pretty easy, just adding and subtracting and sort of memorizing the empirical rule. So let's go on to do some more problems. Oh, but before more problems, we're going to just look at this in terms of a shape analogy. just to sort of cement it in, when we think about shapes like rectangles, we know that rectangles are sort of defined by their length and their width. If you know the length and their width, you could draw that rectangle. In the same way, for the normal distribution, all normal distributions follow the empirical rule. So all you need to know is the mean and the standard deviation. I'll write that here, standard deviation. And you could draw that particular normal distribution. And we know that it's unimodal, symmetric, asymptotic, and continuous. Now, rectangles can all look a little bit different. Like sometimes their length is longer than the width, sometimes the width is longer than the length, sometimes the length equals the width in the special case of the square. So they could all look different, but they're all rectangles. In the same way, normal distributions can look slightly different from each other because the x-axis can be stretched out or can be shrunk. But as long as that normal distribution follows the empirical rule, where about one standard deviation out on either side is about 68%, then you know, hey, this is still a normal distribution, even though it might look too skinny or too fat. So what can you find out when you know rectangles, right? Well, if you have the area and the width, so let's say you have this and this, you could find out the length, right? Because they have these relationships with each other. Same thing with perimeter. If you know the perimeter and let's say the length, then you could figure out the width, right? And these are what we call constraints. They constrain the system. They're like these little boundaries. And so you sort of can bounce within the boundaries and figure out the things that are missing. In the same way, when you have normal distributions, you could bounce from probability to raw score because they have this relationship. And that relationship, the one that you know for now, is called the empirical rule. Now, we've only covered knowing the relationship between probability and score only when they're at even intervals away, right? So like 1 standard deviation, 2 standard deviation, 3 standard deviations. But right now we don't know how to get probabilities when it's like 1.5 standard deviations away, right? And that's what we'll cover in the next lesson. Now let's go on to some problems. Okay, so example 1. Using the empirical rule, what percentage of values in a standard normal distribution fall below the z-score of -1, or what falls above a z-score of -1? And although we haven't quite covered the standard normal distribution yet, let's assume that it's the normal distribution we've been talking about. We'll define it in the next lesson. It's actually when you don't know any of the values and you just know the z-scores or or what we call the standard deviations, right? So that's what the z-score is. All right, so we could easily do this problem just by knowing the empirical rule. And in a standard normal distribution, we pretend like we don't know the actual values. Well, you don't have to pretend, we really don't know. And instead, we just know the standard deviations, or what we call the z-scores. Okay, now what they want to know is what percentage of values fall below a z-score of -1. And here we know that this area is about 14%, and this area is about 2%, right? And this area is pretty negligible, right? So if we add these up, that would be 0.16. So that, to write it in sort of formal algebraic expression, is P, where Z is less than -1, equals 0.16. Now, once you know this, now it's asking, what about above a z-score of -1? So now it's talking about this area. Well, there's 2 ways you could do this. To figure out P, where Z is greater than -1, we know that the entire area is 1, right? And we could just subtract out this red part, 0.16, right? We could just do that. And we know that that will end up with this area, which will then be 0.84. There is another way we could do this. What we could do is add up this part over here, which we know is exactly half of the normal distribution, so 0.5, and then add to it this little part right here, which we know is 34%. So when we add those together, so we could do 34, and that also gives us 84% of the curve, right? And so those are just two different ways of doing it, either way, whatever your preference. Okay, so here's another example. Using the empirical rule, what percentage of values in a standard normal distribution fall below the z-scores, or standard deviations, of -1 and 2? So let's draw it out again. It's nice to sketch it so that you know like where you're headed. Here's 0, and what we need is between the standard deviation of -1 and 2. So once again, there's multiple ways you could find this out. Probably a really simple and sort of straightforward way is knowing, so P, we're really trying to find out P where X or Z lies in between -1 and 2. And what we really could do is add up all of these separate little probabilities. So probability between -1 and 0, and add that with the probability between 0 and 1, and add that to the probability between 1 and 2, right? We could just add those all up. And that would be 34, 34, and 14, right? So 34, 34, and 14, right? And that would give us 68, 70, 82. 82% of the curve. That's one way of doing it. Another way you could possibly do this is, one way is I just know that this is 2%, right? So I could deduce that from this whole thing being 50%, I could just subtract that 2 and get 48. And so I could actually just do 34 plus 0.48. And that gives me the same answer of 82%, right? So just different ways of cutting this up, figuring out the distributions. Some of you may just memorize that the middle part between -1 and 1 is 68, so then it would be 68 plus 14, right? So either way you want to do it, but the point is I want to show you there's lots of different ways you could cut this up. You want to think of these normal distributions as like sort of break-offable, like like a chocolate piece or something, where you could just break it off in lots of different ways and add them together again in lots of different ways. All right, so example 3, what is this problem missing? And sketch and find what is missing. Now we know that there's only 2 things that could be missing in the problems that we've introduced so far. One is probability, that could be missing, or the value, the boundary. All right, so it says, given a normal distribution with a mean of -25 and a standard deviation of 10, find where the middle 95% of values will lie. So right now we have the probability here, right? What we don't have is the actual values. So this is a value missing problem. So that's what we're going to need to do. It helps to sort of sketch out where we're going. Okay, So my x-axis is a little bit off. It's a little too far south. Okay. We know that the mean is negative 25. So here are my raw scores. And here I'm going to write my z-scores, or standard deviations. Here's 0, negative 1, negative 2, negative 3, 1, 2, and 3. And we're trying to find the middle 95%. And if you remember the empirical rule, we know that around here and here, this is approximately 95%. And if you want to check that, you could add 34, 34, 13.5, 13.5, right? And that's about 95% of the curve. So let's try to find what these values are right here. What are these values? Now, we know that the standard deviation is 10, so each of these little jumps are worth 10, right? So let's go out 2 jumps from negative 25. So that would be negative 35, negative 45 on this side. And if we go in the positive direction, it would be negative 15, negative 5. So to solve it, we would say this probability, 0.95, is the probability between negative 45 and negative 5. Now, another way of writing it without these values is to write it in terms of the standard deviation. But it asks about values. But I just wanted to show you this other way. So the other way we could write it is also like this. So what z-scores does the middle 95% cover? And that would be between 2 and negative 2. Note that the 45 corresponds to negative 2, and the negative 5 corresponds to positive 2, just like here. Right? So that's the nice thing. There are these relationships between the raw scores and the z-scores, and we're going to get more into that in the next lesson. Now here's example 4. What is this problem missing? Sketch and find what is missing. Given a normal distribution with a mean of 46.4, and a standard deviation of 6.1, find the score that cuts off the largest 16% of values. So this one gives us, again, the probability, and we need to find the score, or the value. So we know that the missing thing is the missing score. Now, using our empirical rule, we could find what that 16% is. Here's my raw scores, and here are my z-scores, or standard deviations. And since I'm looking for the top 16%, I need to go on this side. 0, 1, 2, 3. And we know that this is about 14%, and this is about 2%. So here's my elusive 16%, right? And I need to find this cutoff score, right? Now, that cutoff score is 1 standard deviation away. And here, my standard deviation is 6.1. So my little jump is 6.1. So all I need to do is add 1 jump to 46.4. So that'll be 52.5. Right? So what we could write is the probability where x is greater than 52.5, that's our 16%, right? All right, so that's it for using the empirical rule to find answers to normal distribution problems. Thanks for using educator.com.